Today's presentation will focus on MotorSolve, which is just one of the many software packages available from Infolytica Corporation. Just a couple of key points about this tool. It's a template-based design software that uses an automated finite element analysis engine to determine the results of the motor you are designing and analyzing. The interface is very modern and is one of the key points we like to mention about this package because it makes it very intuitive to use. The automatic winding layout feature automatically presents a list of all balanced windings, and again, another key point we'd like to mention because it is a very novel feature in this package. There are several analysis strategies available in MotorSolve, particularly MotorSolve SRM, and I'm sure Adrian will cover that in his presentation. And there are other features related to simulating both the motor and drive and summary and reporting that Adrian will no doubt cover. So at this point, I'd like to pass things over to Adrian, who will be giving the bulk of today's presentation. Thank you.
Good afternoon, ladies and gentlemen. Thank you, Chad, for the introduction. As Chad mentioned, we're going to talk about MotorSolve, but specifically as it pertains to switch reluctance motors. I'm going to step through the interface associated with the steps that you would need to take in order to set up a machine and to set up the experiment that you desire, and then to execute that experiment. So this is a view of MotorSolve when you initially open it up. And it's split into three basic areas. We have a main control area up here on the left, generally represented by a tree and with pluses and minuses for expansion. We've got a detail area down here on the left with various text fields and pull downs and things that you can use to configure the machine. And then on the right, you'll have your visual feedback for either the geometry or the layout, or when we get to it, the actual solution. So the first place that you come to with regards to the design of the machine is the template sort of design area where you would enter the supply voltage, rated current, rated speed, and then the overall geometry envelope. So in this instance here, we've got an outer diameter for the stator, we have an air gap, and we have a stack length. And then further, as we look down here, we have an option for the number of and nature of the actual poles for both the rotor and the stator. With simple pull down, you can see the various options here for typical sorts of machine setups for the numbers of poles for both the rotor and the stator. And on the very bottom here, you can see that there is a manual option, which would allow you to enter in the number that you would like for them independently. Also note that there is a separate field for the number of phases, and MotorSolve is able to handle 3, 4, and multi-phase for the setup of the stator. Once you've declared the basic setup and nameplate type of information for the machine, you would then go into the specifics. And as Chad mentioned, there's a very nice futuristic interface which allows you to enter basic text fields, basic values in text fields, for how the machine should be configured. And so, for instance, we can go in here and let's just, for instance, add radius to the base. Now, note also as you're doing this that there is a visual representation of the parameter that we're going to talk about or change. And with a simple text value, you can see that we've modified this text field and we get the visual feedback associated with changing that parameter. At any point in time, if you like, you can use the control left click to zoom into the structure, or you can double click to click out, and then also with a single click of the left mouse and a drag, you can change the perspective and get a full 3D representation of things. Once we finish configuring the rotor, we then go in and do the same for the stator. And you can see that there are a few more parameters associated with defining the slot for the stator. Note also that the tooth does not need to be parallel. We can change the values to represent anything that we desire with regards to that. And by simply changing these text field values, you can configure the machine to your desire. Once you've configured the geometry layout, we then go into the winding area. And so you can define the various ways that one might like to construct the winding, or the nature of the conductors in the slot. So first off, let's note that there's actually a liner, slot liner that exists, and there's also a separator that exists, and you can change these values to depict the real nature of things for the actual design. You can change from amongst a wide variety of different conductors, and here we have a pull down which talks in general terms of a fill factor, typical kind of a strand size or diameter, or you see here various standard gauge wires to pick from. In the example that we're going to show today, we actually have rectangular cross-section wire, which is somewhat thin compared to the length or the width. Note also that you can define whether there's more than one strand in hand as you do it, decide what's in the winding, as well as the number of turns. Now, as my colleague mentioned, you have the option for accepting the automatic layout shown here for a standard three-phase kind of a switch reluctance machine. However, you could choose to use the manual option, and in so doing, choose the go and return for each of the components or parts of the slot that you wanted to design, depending on what you're actually exploring. The final geometry setup has to do with the conductors and the lamination along the shaft. And you can note here that there's a default length of the end winding. There's also a default diameter associated with that. And you have full access to change that. And in so doing, the electrical or the conductor-based parameters will change. And I'll jump back to this window for just a moment and talk about what we present here. We present both an inductance and resistance for the winding and the end turn areas, as well as a representative fill factor. So these three basic areas are what will decide the geometry and the setup for your desired machine. And once we've completed setting that up, we would then go into a material property area where we have various materials represented and can select and choose from amongst the library and assign the various materials. And here you can see that I have represented 4 materials in the device or in the machine. We have copper for the windings. We've got an epoxy resin associated with the separation amongst the coils. And then we've got an M19 associated with the laminations. It's instructive to note that Infolytica encourages you to accumulate your own material data. However, we do provide a library, and it's fairly extensive. In that library, for most materials, you're going to talk about a mass density, maybe some thermal properties, For nonlinear steels, like you might have in a lamination, we're going to require a DC-BH loop, shown here. And then, very, very importantly, we also need to define and have demonstrated for this sort of material the core loss representation. And note here, as I slide through this, that we have a series of different frequencies ranging from 50 to several thousand hertz. We also have various thicknesses represented. And for each one of these curves, you can see a set of data values provided by the manufacturer in red. You can see a mathematic curve fit, which is shown in blue. And then MotorSolve automatically splits this core loss or iron loss for the global or material properties for the steel into two components using the Steinmetz equation. And so we also represent the hysteresis and the eddy current losses separately. This allows us to understand and know, especially when we get to the solution stage of things, how it is that our machine is going to function and where we're going to get losses and how we might want to address those or reduce them, and then also how these losses actually manifest themselves in thermal energy or heat, which is derogatory to the performance of the machine. Okay, so now we have set up the geometry, we've set up the materials, and now let's go over the basic set of experiments that we have. As you look at the product, if you were to roll over, as I have, the flux linkage test, you can see here that we've got a broad window that pops up and tells us a little bit about that experiment. If we look at the very bottom here, we've got a nicely described methodology for what's going to occur and what we might get from this response. And at any point in time, if you have questions, you can hit F1 on your keyboard and get additional help and constructs to assist you. Well, this basic experiment, which I will now run for you, will provide us with the flux as a function of the assigned and rated current, as well as several depicted rotor positions. You see the progress on the bottom, shown in steps here. And so for each of the various currents, from 0 to rated current, which is 300 amps, you can see here that we have a range of flux values in Webers. So we're presenting the flux linkage from the aligned up here at 0 to the unaligned down here at 22.5. Likewise, if I were to desire to go and do the inductance, simply click on the inductance. I see here that I have another set of parameters to define. Again, we're going to step through the current and the rotor positions. And the solution will present itself in a very nice graph. At any point in time, if you were to click on this vertical bar, you have, with your left mouse, you can slide through the graph. It depicts and shows the intersecting value of the vertical line with each of the curves. It clearly represents that to you. Additionally to that, if at any time you want to, you may click on this View Data button. And this View Data button will show you the tabulated data. Additionally, you can export this data directly to Excel or to a ASCII text file. Or one very handy feature in MotorSolve is that you can add it directly to a report associated with the model file. And as you step through your set of experiments, you can sequentially add the various experiments or setups that you like to this report. And at the end of your experimentation, you can export this report directly to a PDF file that you can use for other purposes for documentation and archiving of your experimentation. Now let's actually look at the torque response of this machine. So if I go into the torque response, note here that we have a new set of parameters. And here we're going to step through from 0 to 180 degrees rotor rotation with 100% current, or 300 amps. And we're going to do that in steps at 22.5 degrees. So here we see the torque response of the machine as a function of the rotor position. And again, we can look and see with the rotor angle of 0 up to 22.5 what the overall torque response will be. Again, we can span through this and get a feel for how things change as a function of either the rotor angle or the actual current. And this will allow us to make value judgments for things like the thicknesses of the steel or any sort of drive that we're looking at. So now let's actually look at the torque speed curve, or the response of the torque speed curve for this machine. And in this setup, there's another feature which is very, very important, and that is that you can actually enter the firing angles. A very important aspect of the switch reluctance machine is to be able to control the on angle and the off angle for the firing for each of the phases as the machine rotates. This is what might control motoring or generating, for instance. But you can see here that we've actually imported and set up firing angles for each of the various speeds, and then we step through and have denoted and will show the torque speed curve for this machine from 0 to 3,000 RPM. And you can see here that over in the operating range, which is roughly with 1,000 RPM, we have just under 1,000 Newton meters, and fairly broad range for that. And a little bit of a roll off after, say, 1,200 or so, 1,250 RPM. Now you can also change the range of what you want to do. So we went from 0 to 3,000 here. And if you were to change that slightly and look at it a little bit different, I've got a different range that I'm looking at. I'm going to go from roughly 0 to 4,000 RPM, increments of 25. So a little bit broader range response. And so now let's actually look at the static response. In our static analysis, we have a series of things that we can ask for. We can ask for the torque, the current, the flux linkage, the co-energy, and the energy, and the inductance. In this case here, we're just going to look at the torque and inductance. Here you can see that you have the choice of entering either the rated current which would default to 100%, or some other value. In this case here, this would allow you to explore and experiment perhaps with a higher rated current or a higher current than the rated for some particular operating point that you might have. But you can see here that we've split the current interval from 0 to 300 in increments of 60 and plotted. It's a little bit busy, so I'm going to take the inductance off for a moment. But you note fairly quickly that by changing this, there's an interesting part about the solution, and that is that the solution that we have run is cached. And so this is another really nice feature which reduces the amount of computation time that you might have, and that I can change my overall experiment and the parameter that I'm looking for as a function of the solution simply by changing and looking at a new construct, and I don't have to resolve. It simply looks at the data which was cached and gives you the appropriate response. Another solution that you can do is our motion solution, our motion analysis solution. And what I'd like to underscore before I actually continue with this particular experiment is to tell you that part of the experiments that you see in this results area are a combination of analytical solution and finite elements, and finite elements, strict finite elements. So this motion analysis is a strict finite element where we're actually going to do a time transient and give you the full transient physics as a function of the response of the machine. These other remaining above experiments are a series of finite element solutions cleverly chosen, and then we've extrapolated and utilized analytical relationships to develop the physics and the response of the machine. So these are generally going to be considered faster solutions, and the motion analysis will generally be considered slower because you're going to do a full transient. But that's another feature of the software, in that we allow you to do your own scrutiny of accuracy of the solution as a function of the time that you'd like to have the solution take. And just as a representative example, I've plotted the torque here, the transient torque, from rated speed up to 3 times rated speed, and as a function of the rotor angle, incorporating these on and off or firing angles. And you can note again that as we use this vertical bar, we track through the data and show the performance of the machine. While I'm here, I'll take a moment to describe the fact that another part of what you can actually do as you're doing the finite elements. I mentioned the fact that you can trade off between the analytical relationships in combination with finite elements or finite elements only, but within the finite elements as well, you have the option for toggling and adjusting the accuracy versus time associated with your simulation. In general, you shouldn't need to move this more than down to 2 or 3, I would say, but you have the option based on the amount of scrutiny that you want to place on things for determining the solution. One other very interesting construct that we've put into the interface is that you have the option in many places to enter either a list or a range of values. So note here that I've chosen to start at 100% of the rated speed and go to 300% in increments of 25%. If I switch this to list, it shows them individually. I could have typed them all individually if I desired, or I could actually go in here and delete one of these or change the value slightly. But just to underscore that you have a variety of different ways of entering the information and controlling the experiment to give the desired result that you have. So now one of the more interesting parts of the ability that MotorSolve has is that when we combine the template interface, which allows you to enter the geometry and to easily construct your machine, we have allowed you to go in and then review the actual microscopic physics. So in so doing, I am actually going to depict for you a series of constructs that you would want to see in order to evaluate the performance of the machine. And the initial set of these I'm going to show is the current density. So if you look at this shade plot that we have here on the right, we're going from minus 20 amps per millimeter squared to plus 20 amps per millimeter squared. And we're showing that with a rotor position of 0 and the timing sequence of the transient solution from the motion analysis. And you can see here that I've got some conductors that are basically off. I've got some that are very high in a plus orientation and some that are very high in a negative orientation, consistent with a three-phase excitation. But if I go and I rotate in position, or effectively time, and I change to an alternate position, which is essentially 22.5 degrees from the first one, then you can see that the current densities have been modified, and the locations of the various peaks and minimums, or maximum minimums, has changed consistently with the rotation and the timing. And just to underscore that, one final, we're going to look at what would happen at 45 degrees. And so you can see here that with a rollover, also I would like to add this as well. In our solution area, I have a very nice capability to roll around, move the mouse, and at any point in time or place, I get a very clear indication of the actual value that I've presented on the screen. This too allows you to scrutinize much more closely as you're evaluating things. Now you see here that there's quite a few constructs that you can review. And the next one that we're going to look at is the flux density throughout the machine. In general, looking at the flux density is very helpful and allows you to scrutinize and get a good feel for the performance of the machine and the utilization of the steel in particular. And to do that, I have plotted two things in this graph. The first I'll call the flux function, but it's basically the flux lines associated with my various poles. And you can see that along with that, when I have a very high density or concentration of those lines, my color, which is up in the area of 2, changes consistent with the flux density close to 2 Tesla. I've set the range purposely from 0 to 2 for constructive assessment as we look at things. And you can see here that we have quite a few places of symmetry in the machine, which you would expect. We have places where we have very high flux density. We have places where we have very low. Again, with the rollover, I can see that my flux densities are on the order of 2 Tesla, implying that for this short instance or instantaneous time, that this area of the steel would be saturated. Now, if I look at additional time associated with that solution, I've rotated the motor by 22.5 degrees, and you can see here that now I have actually very little flux density comparatively speaking, from the previous graph. In the actual teeth area of the stator, I have a couple of little places, but nothing as significant as the previous one. And because of the constructive flux addition at this time instance, I now have saturation out here in my return path for the stator. I'll show one final flux density. And so this is at 45 degrees rotation, and you see the same sort of clear picture of the flux density. Gives you the ability to scrutinize and determine, well, do I have enough steel here? Do I need a little bit more? How would I go about it? Is it necessary given my performance? And so now I'll actually summarize the performance of the machine by going back to the motion analysis. And we have here a table which summarizes this performance of this machine. And so, for instance, we have 958 Newton meters of torque on the shaft. Our input power was 106 kilowatts. The output power is 100 kilowatts. We have an efficiency of a little over 94. You can see here that I've got torque per unit volume. I've got just under 12 newtons per square inch as my stress. And one very interesting feature of this software is that I have a completely broken down or separated into parts notion of the losses for the machine. So in this case here, we have just under 6 kilowatts of loss. Doing strictly I squared R losses, we have 3.5, so it is a majority. However, what's very instructive here is to actually look at the breakdown in the losses as a function of both the teeth and the back iron for the stator and the rotor. And also note that if you recall from our discussion about materials, we have cleanly distributed or broken the losses in the lamination into their hysteresis and eddy current components. And we have almost 4-to-1 in the hysteresis losses to the eddy current losses in the stator, and it's more like 5-to-1 in the rotor. So this is very instructive because this helps to tell you which are more important with regards to the frequency and the drive, and to help clarify for us what we might want to do to reduce the flux densities or to modify materials and to optimize with respect to our flux density versus the generated losses that we might have. This underscores the capabilities of our switch reluctance motor technology in MotorSolve. And at this point, I would like to turn it back over to my colleague, Chad, to share any of your questions. So we're going to open up for question and answer.